Welcome everyone. Thank you for joining us today for the JKMRC Friday Seminar for the 6th of August. My name is Nathan Fox from the Brian Research Centre at the SMI. Thanks everyone for joining us online. I'd just like to say before we begin, on behalf of the University of Queensland, we acknowledge the traditional owners and their custodianship of the land on which we meet today. We pay our respects to their ancestors and to their descendants who continue cultural and spiritual connection to country. We recognise their valuable contributions to Australia and global society. It's a pleasure today to introduce today's speaker, Dr Simon Jowitt from the University of Las Vegas. The University of Nevada, Las Vegas. Simon obtained a BSc degree in geology from the University of Edinburgh in the UK, an MSc from the Camborne School of Mines, and a PhD from the University of Leicester, before joining Monash for an 8-year stint as a postdoc and lecturer. In 2016, Simon moved to his current position as assistant professor at the University of Nevada, Las Vegas, focused on economic geology research and teaching. So like most economic geologists, Simon necessarily has very broad research interests, and these span ore deposit formation, mineral economics and exploration, critical metal resources, and the geochemistry and mineralising systems. Impressively, since 2010, Simon has published more than 85 papers, and he's on the editorial board of Economic Geology. And in 2014, Simon was awarded the prestigious Society of Economic Geologists Waldemar Lindgren Award. Today, Simon is going to tackle the topic of climate change mitigation and critical metals, future challenges and opportunities for the minerals industry. Certainly a very relevant talk. For those of you online, before I do hand over to Simon, if you could type questions towards the end in the question and answer box, and then we can pose those to Simon at the end. So without further ado, Simon, over to you. Thank you.
Thank you for that, Nathan. I'd just also like to, the University of Nevada, Las Vegas would also like to acknowledge and honour the indigenous communities of this region here in southern Nevada, and recognise that the university is situated on the traditional homelands of the Nuwuvi Southern Paiute people. But as Nathan mentioned, I'm going to try and tackle some of this pretty large topic of climate change mitigation and critical metals, and metals in general, in fact, and talk about some of the future challenges, opportunities, and potentially drivers for the mineral industry over the next maybe 20 or 30 years if things pan out as we think they're going to be. But I'm going to start out by being a bit inflammatory. Mining is old, dirty, problematic, and we don't need it, right? This is Bingham Canyon, just outside Salt Lake City, one of the world's biggest copper mines, and this is what people think of when they think of mining. A big, dirty hole in the ground with no relevance to modern society. Now, hopefully no one in this audience actually agreed with that statement, because, we all know that is essentially wrong. Mining has been and will be vital to modern life and society for centuries, and will be even more so into the future. We need mining to reach some of the UN Sustainable Development Goals and mitigate against climate change. But the fact is that comparatively few people, even fairly few in Australia in some cases, certainly a mining state like here in Nevada, comparatively few people acknowledge or even think about it. If you look at the IMARC conferences a couple of years ago in Melbourne, people protesting about mining and not realising how vital it is to their way of life. And people think that mining is dirty, harms the environment and people. That may be the case. Mining companies do a better, I'm not going to say perfect, but a better job of environmental assessment and cleanup than in the past. They're more socially aware, and they're having to be, because otherwise, they're basically not being allowed to mine in some cases. Mining can and should provide communities with benefits. But one of the important things that we're going to see into the future is that any meaningful climate change mitigation and limitations of CO2 emissions, in a significant way, requires mining, and more mining than we've ever done in the past, most likely. And I'll show some data to go through that shortly. But before we get into that, just a brief reminder, not that you all need it, but just a brief reminder of why modern society needs mining. This is something that the Minerals Education Coalition over here in the US produces each year, the Mineral Baby. It basically outlines the per capita consumption of metals, minerals, and the like per American per year. So every American born will need 3.19 million pounds of minerals, metals, and fuels in their lifetime. I've done the metric conversion here, and obviously the US standard of living and US consumption is slightly different to other countries around the world. But you're talking 430 kilograms of copper per capita for every American, nearly more than a ton of aluminium, nearly 400 tons of lead, getting on for 220 or 230 kilograms of zinc, and so on. So there's a significant amount of metals and minerals consumed or used per capita in every country in the world. Not just, this is America, every other country would have probably slightly lower numbers, but still significant. Equally, the devices you're watching me on, because everybody's, I believe, locked down in at least Brisbane and maybe Melbourne now as well. The devices we're all participating in this webinar on way more mineral and metal intensive than similar technologies, if they even existed, say, 20 or 30 years ago. And we can see here's a 1980s standard unsmartphone and here's a modern smartphone. The range of elements compared to here and here, you see a significant increase in the number of elements that's added into this one device. The only losses have been really beryllium and lead. Everything else has been added, or at least the makeup of the number of elements used in these devices that we consider run-of-the-mill, considered to be part of modern life, has vastly increased over the last 20 or 30 years. And this is just, I'm sure you've seen similar diagrams like this, but if you want a touch screen of any technology, any type, you need things like indium, tin, and oxygen. If you want glass, you need aluminium and silicon, oxygen, potassium, rare earth elements used in colors in the smartphone screen. You need a lot of copper in electronics as well as other metals. So this is just, the sheer complexity of the modern technologies that we consider to be routine means that they use way more elements than we've ever used before in significant amounts. And the fact is that those elements almost always need to be mined, especially if the demand is increasing, we can't meet that demand by recycling. Similarly, if we think about climate change, and I'll touch on this later, but if we think about kind of low and zero carbon dioxide energy generation, you take a simple wind turbine, you need aluminium, rare earth elements for the magnets in the generating system, copper, steel, concrete, zinc, molybdenum, and so on. These things we're going to need to mitigate climate change are not going to just appear out of the middle of nowhere. They need to be produced from materials that we need to essentially mine or extract from the earth. So that's just a few examples of the things we take for granted as part of modern life require metals and minerals. And you all know that in the audience here. Now, minerals and metals are the material basis for modern society. And that's why we need mining. That's why mining is important, has been important, and will continue to be important if we want to live a modern lifestyle. This, combined with increases in population, in other words, the material or mineral intensity of modern life, combined with increases in population, is the reason why we mine more minerals and metals than any other time in history. It's an underlying trend. It's been present for the last century plus, and it's present for, in almost every metal or mineral you look at. I've got a few examples here. I'm not going to go through them in detail, but if anybody wants any papers, I can provide these. This is gold. So this is just looking at gold production from 1913 to about 2015. You can see producing at 1913, maybe 700 tons of gold a year. And, now we're going up to 3,000 tons a year plus. Just the same situation for copper. Copper, we're mining more than 20 million tons of copper a year. Similar zinc, we're going up to this diagram only goes up to about 2012 or so, but we're heading up north of 15 million tons of zinc a year. And this applies to almost every other metal you look at. And I'll show that in one example here. The diagram here is a little messy, but basically what we've got here is you've got production data for a wide variety of different metals, things like bauxite, iron ore, cobalt, gold, molybdenum. We've got all these metals, and they're all normalized to 1956 production. And what you see in every single metal or mineral is a general upward trend. Some of these upward trends are far more rapid. So, like, if we look at things like the rare earths, we're using way more rare earths than we used in 1956. Unsurprisingly, some other metals are very variable. But one thing you'll see is that we mine more of any of these given metals or minerals than we did in 1956, often significantly more, 10 times more in the case of some of these metals. And it's not just the volumes of materials we're extracting, it's per capita. So in other words, if you compare that production or the production statistics for these metals, you compare them to world population, and what you see is we actually consume more metals per head than we did in say 1956 when these data begin. And in some cases, like the rare earths, we use 10 times more rare earths per head of population than we did in 1956. So it's not just increasing amount of production, it's actually increasing amounts of consumption relative to increasing population, if you like. And that just shows how materially intensive or metal and mineral intensive modern society is compared to 60 or 70 years ago. And presumably, unless something significantly changes, these trends will not significantly alter. We're going to see increased amounts of population, we're going to see increased amounts of demand for metals, and we're probably going to see increased amounts of per capita demand overall for some of these metals as well. So we mine more than we ever have done before. Does that mean we're actually running out? There's a kind of slightly inflammatory question. One thing, this is a paper from last year that myself, Gavin Mudd and John Thompson put out, that we basically looked at ratios of reserves to productions for a variety of different metals. In other words, these numbers on the left here are essentially estimates of how much years you have left of a certain mineral if all you have is in those reserves that you know about. What you see is that data are a little noisy here for all of these different metals. You know, we've got base metals, we've got bulk commodities, precious metals, and specialty or critical metals in some cases. The data are noisy, but that probably just reflects uncertainties in the data rather than actual significant variations. But what you see is everything is kind of coming down here and flatlining and forming fairly flat trends. What does that mean? That means that we're producing more than we ever have done before, but that production is being matched by increasing the amount of reserves. So in other words, we have a constant between the amount of reserves we know about and have been delineated and the amount of production we have. So what we see is we're not effectively running out of anything if you look at these data, but exhausted reserves are being replenished by delineation of known but not previously formally quantified mineralization. And that's the way that the mining industry works. But one thing to note is that we might know that within economic geology, the minerals industry, but a lot of other people don't, and they take these numbers and they go, oh God, we're going to run out in 50 years. Whereas if you look at the time series data, the general indication is that things are a fairly steady state. Equally, again, this is data that Gavin Mudd and I put out a couple of years ago, maybe 2018 in economic geology. This just looks at known copper mineral resources in terms of million tons. So here we have copper resources in 2010, copper resources in 2015. We actually calculate, we incorporate production. So in other words, these are 2010 resources minus production. What we can see is that if you plot all these data up, you get a fairly distinct trend, and that trend has a slight positive skew to it. In other words, if you look at a given resource in 2010, that resource might have had some production associated with it, which we account for. But in 2015, it's likely to be around 13% bigger than it was in 2010. And this is the effect of brownfield expansion. So not only are we discovering new things, discovering new mineral deposits, the deposits we know about are actually expanding at a faster rate in some cases, or in quite a lot of cases, as you can see here, than production. So all of this says, you know, we're not actually running out. So we're producing more than we ever have done before. We're actually delineating more resources, both in brownfields and greenfield situation. Resources and reserves are keeping or keeping pace with or outstripping production. So in other words, it's all good for the minerals industry, and we're not going to run out, right? Unfortunately not. I mean, there's this big elephant in the room called climate change that I'm sure everybody's heard a lot about. And to mitigate effectively against climate change, we need to reduce the amount of anthropogenic carbon dioxide and other greenhouse gases we put into the atmosphere. How do we do that? We need to move to essentially low and zero carbon dioxide transport, energy generation, and we need more energy storage and infrastructure associated with that. More electric vehicles, more solar and wind power, and so on. So the bottom line is, if we want to do that, if we want to meet carbon dioxide emissions targets, we're going to need more mining. More mining and more recycling, but certainly more mining than we ever have done before, and more mining of minerals that we probably haven't really thought about a huge amount in the last 20 or 30 years or so. So, one good target is the IE, International Energy Agency's 2-degree temperature increase target, which limits emissions up to from 2015 to 2100 to 1,000 gigatons carbon dioxide. Current annual production is 33 gigatons a year, equating to basically 3 times our target. So we need to reduce carbon dioxide, or we need to decrease 60% of current by 2050, decline to neutral afterwards. What we need to do that is a rapid rollout of renewables, low and zero carbon dioxide transport, and increased amount of energy storage, and all of the infrastructure that goes with that. So that's one thing. The other thing is that it's not just meeting carbon dioxide emissions or climate change targets. We're seeing consumer investment demand move this way already. Consumers are getting more interested in electric vehicles. Renewable energy costs is coming down, which is actually driving up demand for that. So what's happening is you've got these 2 forces. One is global climate change mitigation, and the other is consumers and investors who are saying, well, we want to move this way anyway. So, what we're actually doing is, what we think is going to be happening is this is going to be the main driver for the minerals industry over the next 20 or 30 years plus, potentially. Because if we want to do anything meaningful about climate change, we need to do this. But equally, if investors and consumers are saying we want to do this anyway, then that's going to be a coincident and kind of a further driver towards this increased metal demand that I'll discuss shortly. If we take electric vehicles as an example, one, they require more metals than petrol vehicles. It's slightly different makeup of metals, but in general, they're heavier. They're heavier. They require more metal for the batteries and so on. And there's equally no point having an electric vehicle that's fueled by coal-fired power stations. It's worse than having a gas-guzzling petrol SUV. So, it's all very well and good. Joe Biden today talking about, well, half the cars produced in in 2020 in the US are going to be electric. That's great, but, we need to actually provide them with low or zero carbon dioxide power. Otherwise, there's no point in doing this at all. Some people might say, well, I don't care. Anthropogenic climate change doesn't exist. Again, hopefully that doesn't apply to this audience, but it does apply to some, both policymakers, the general public, fairly influential people in some cases. The first thing to say is that science doesn't really care what you believe in. The vast majority of scientists and researchers are fairly convinced by the argument that anthropogenic, carbon dioxide emissions are the likely cause in climate change. Secondly, the shift is happening. We're moving to low carbon dioxide energy generation and transport. They're both becoming cheaper. They're both becoming more attractive. So these changes are happening already. It's a global movement, and it's a trend that's going to continue. It's being driven by consumer sentiment and investment funding. And the last thing to think about from a kind of country-specific viewpoint is metal mining, processing, green technology, energy development, and more, all involve the production of high-value raw materials and have the potential to generate a lot of well-paid jobs. If we do see this transition to low and zero carbon dioxide energy generation and so on, that's going to be a mining boom. And you can either get on board and accept that it's going to be a mining boom, or you can kind of ignore it and keep on digging up low-value coal, to be fairly inflammatory again. But, we can have a think about cars as a starting point. So, here's a few different cars, and we're just looking at copper here. Copper is a fairly ubiquitous metal. It's used in normal internal combustion engine-driven cars. It's used in hybrid electric vehicles, and it's used in battery vehicles. But the one thing to note is that electric vehicles are heavier, but they've got way more copper in them than an internal combustion engine. You're talking 4 times as much copper in an electric vehicle than an internal combustion engine. And that's just one metal. If we do a back-of-the-envelope calculation, a global vehicle production uses about 1 million tons of copper per year, or about 5% of global copper production. Only 1% right now of these new vehicles are electric. Targets for countries to move it to all-electric fleets by 2035 to 2050. If we say things are a bit slower, world agrees to go to all-electric vehicles by 2060. Electric vehicles need 4 times as much copper as petrol vehicles. If we go all electric and have all electric fleets by 2060, the global car industry is going to need about 4 million tons of copper production a year, assuming no growth in new vehicle demand. And that's 400% increase from now, or 20% of current global copper production. And it's more, because where are you going to charge these vehicles? You need infrastructure to charge the vehicles, infrastructure to connect renewable energy sources to these charging points. And this is just transport and copper. If we actually think about energy generation and other sources, then the amount of metals we're thinking about here starts to become pretty staggering. This is just lithium-ion battery packs in passenger electric vehicles, 2018 to about 2030. Looking at that based on electric vehicle outlook 2018 data. You're talking about less than a million, well, less than a million tons of materials, metals going into lithium-ion battery packs in 2018. We're talking 8 million tons of manganese, lithium, cobalt, nickel, graphite, aluminium, copper, and so on, just by 2030, considering we're going to go to all electric fleets by 2035, 2040, and so on. And if we think about energy, because it's not just the vehicles, it's the energy that's needed to power the vehicles. If we're going to go to all solar and wind and renewable, this is the kind of change that we're going to see in demand for a range of different metals, just based on energy generation alone. Not the infrastructure associated with transmitting that energy, just the energy generation capacity alone. This is 2050 annual demand from energy technologies as a percentage of 2018 production. You're talking 500% increases, 400% increases in graphite, lithium, cobalt, 200% in indium. Even copper is a significant percentage of annual demand from energy technologies as a percentage of total 2018 production. And annual demand from energy technologies in millions of tons, 5.5 million tons of aluminium, 1.5 million tons of copper, nearly 2.3 million tons of nickel, and so on. And this is to ensure we're rolling out the technologies we need to mitigate against climate change. And as I say, it's not just climate change mitigation, it's consumer and investor demand that's also driving these changes. To put that in numbers, here's our various minerals and metals. Here's our 2018 annual production, 60 million tons or so of aluminium. Projected annual demand, so this is a constant demand, it's not just a one-off, from energy technologies is about 5.5 million tons of aluminium a year in 2050. That's going to be 9% of the current aluminium production. And these percentage values over here, 7% of copper for energy technologies, 18% of lead, 100% of nickel. So in other words, we have to double nickel production by 2050 to ensure we can actually meet these demands from energy technologies alone. This is not the infrastructure. This is not necessarily the electric vehicles. This is just the energy generation capacity. And this is again looking at these are just emission scenarios. So this is essentially business as usual. This is 2 degrees, and this is beyond 2 degrees. So this is what we want to hit, and this is where we really want to be. What you're talking about is, in terms of millions of tons, the annual average demand of minerals up to 2050 is essentially doubling from what it would be under business as usual scenarios. That's a huge amount of minerals and metals that we need, that we're going to have to produce as a minerals industry. So where are we going to get this metal from? We need 3 billion tons of minerals and metals to deploy wind, solar, geothermal power, transition to electric vehicles, and energy storage for below 2 degrees C future. We need mining, we need lots of mining, but that's not the only thing. One, it's not easy to ramp up production of any metal. If you're talking about doubling nickel production, imagine, where is this nickel going to come from? There are a lot of nickel resources out there, but we need to put them into production. The average time for a resource to make it into production isn't very quick. And if this demand starts ramping up rapidly, then we may well start running into scenarios where these major base metals are actually, producers of these major base metals are struggling to keep up with demand. But then there's also another subset of problems, and this is the critical metals stuff I mentioned at the start. So there's a few odd metals like neodymium, lithium, and so on. One of the questions is, where do we get these from? There's a whole range of these metals that are called the critical metals that could be even more problematic for a low carbon dioxide future. This is just a US example. So these are the metals we currently consider critical. Some of them, are fairly common, like aluminium, but then you've got things like, let's say, cobalt, hafnium, lithium, the platinum group metals, the rare earth elements, uranium, scandium, tantalum, tellurium, and so on. I'm not going to go into this in detail. I can certainly pass on the list if anybody's interested in this. List is being updated right now. But some of these metals are not metals we typically think about when you're talking about mining. It's certainly not base metals, these specialty metals or critical metals that are not commonly or haven't been thought about in any significant way up until the last decade or so. What are critical metals and why should we care? There's no strict definition. They vary by viewpoint and what they are. There's no global agreement. But in general, they provide essential properties to a technology or product. In other words, the magnets in your laptop hard drive need rare earth elements. The touchscreen you might be using needs indium and so on. So they provide essential properties that we consider routine now to technologies or products. And this is especially true of low carbon dioxide technologies, electric vehicles. In other words, these elements and metals are hugely vital for climate change mitigation. You can't swap them out. You can't substitute them. They're not recycling. They're not easily recycled. And recycling anyway can't often meet increasing demand. They're subject to supply chain risk. The production is often concentrated in one or two different countries, and they're often strategic as well because these things have military or energy production uses. And the last thing to think about here is that an awful lot of these are not actually produced as main products. Nobody goes out and looks for an indium mine. They go out and look for a zinc mine and then produce indium as a byproduct, potentially. So these, they're often dominated by extraction at smelters, refineries, and it's uncertain what values accrue to the source mine. And that means that mining companies, even though their mineral deposit may produce these metals that are a smelter or refinery, they don't often care because they don't see the value. And that in turn means we have significant unrealized potential for critical metal production. These metals are often lost to waste rather than being produced as a result of economics, mineral processing approaches, and basically insufficient knowledge of deportment. In other words, we don't know where these elements are in ore bodies. We don't know how they behave during processing. And as a result, we can't enhance the production of these without that core knowledge. We also don't know how much there is. The resources are often poorly reported. Numerous mines globally are known to produce these metals, smelters that they send their concentrates to, but they're never stated in resource reserve reporting because they don't. The value just doesn't accrue to the mine. The value isn't significant enough for formal resource reserve reporting. This is an example. This is Nassar and others. The wheel of metal companionality. What we've got here is we've got main metals. So we've got our base metals, iron, titanium, and so on in here. These are what you typically mine for. And this is what's produced as a byproduct. So if you look at zinc, say 75 to 100% of cadmium and indium is produced as a byproduct of zinc production. Similarly, copper, that's where we get our selenium and tellurium from. Aluminium, that's where we get our gallium from. Titanium, that's where we got our zirconium and hafnium from, and so on. So you can see there's an awful lot of by and co-product metals that are produced as a result of mining of other elements. If we put it more simply, here's again, we've got our main metals, and here we've got our co and byproduct metals. What this does is this indicates the sectors of the mining industry that the production of these critical elements are reliant on. Why is that important? Because, one, it gives us targets to aim at if we want to increase the production of these critical metals. If you want more indium, you look at the zinc industry, you look at zinc smelters and refiners, you look at zinc materials flows. But on the flip side of that, if zinc demand drops for some reason, say we develop another approach to galvanizing that doesn't require zinc, there's a sudden complete change in the zinc industry. Zinc demand slumps. That means necessarily our production of indium, germanium, and cadmium will slump as well, which, considering some of these metals are critical and important for things like climate change mitigation, that really could put, this is one of the key kind of things we need to think about when we're thinking about ramping up production of these critical metals. We cannot just go out there and mine indium. We need to mine more zinc, or more correctly, we need to make sure that the indium within zinc concentrates and so on is actually extracted rather than lost. And this just shows the kind of scale of some of the issue. Here we have global production of critical metals. This is just in tons of metal. So these are all fairly small markets because these metals are often used in small amounts in certain technologies, but they impart really important characteristics to those technologies. So you can see this is just the production statistics for 2018. But the other thing to note is the proportion of these metals that are produced as a byproduct of something else. And they're basically all nearing 70 to 100%. One thing to note is that we don't know what proportion of these metals are produced as byproducts of the other metals because we don't have the data. And the other thing for some of these metals, we don't actually have production data. So, we have some data, but there's still some real unknowns there in terms of, how much the proportion of some of these metals that are byproducts and the amount of some of these metals that are actually produced globally. So what do we know about critical metal resources? We're learning more, but few of these resources are well quantified. Lots of critical metal resources have significant uncertainties. Little to no data available for resources and reserves, and even for production. Or you look at two different sources and you have different data for the same year. So there's an awful lot of uncertainties in these areas that we need to quantify before we start to tackle these problems. Because how can you assess the criticality of metal or try and increase its production without knowing where the metals are coming from, without knowing how much there is already? So one of the questions is how can we produce more of these metals and ensure the supply given they are co- and byproducts of other metals? And that's a question that certainly me and a couple of colleagues here at UNLV are working on, but it's a question that needs to be thought about globally. So what do we need to know? I would argue we need to know global resources. We need baselines to ensure we can meet future demand. We can't rely on published resource or reserve data, given the lack of reporting of critical metal production. There's a couple of examples here. The Sierrita mine in Arizona produces rhenium, but that rhenium is not reported in resources and reserves. So we don't know how much, we don't know what the recovery is of that rhenium. Is it good, bad, ugly? We don't know. All we know is that it produces some of the rhenium that's in that mineral deposit. Similarly, Australian lead zinc deposits known to contain indium, but Australian zinc refineries don't produce this in general. Byproduct production is dependent on where you ship and sell your concentrates. And that's economics. That's the price you get for the zinc contained in, or lead, zinc and lead contained in those concentrates. The indium is something that accrues value to the smelter and the refiner, not the mine. So if you as a zinc miner, you're selling your concentrate somewhere, you don't care how much indium there is in there because you get the money back on the zinc, not the indium. But putting this simply, we often don't know how much we have. We don't know where we have what we have actually comes from. Because backtracking things to the smelter, from the smelter to the mine is not always easy. And that, as a result, means we don't often know how to increase production as a result. And that's a question that's going to need a lot more research and thinking about into the next, now basically onwards. This is one example. This is Broken Hill. This is data that Tim Werner and others colleagues at Monash, when he was there, collated, looking at the amount of indium in tailings at Broken Hill. Through the life of the mining there. This is the kind of this is a conservative estimate of how much indium ended up in tailings. This is the kind of optimistic, and what we've got is we've got a range basically from say about 500 tons of indium a year, or 500 tons of indium just sat in tailings at Broken Hill, or maybe up to 3,500. But until you go out there and assess it and think about it and see if it can be extracted, we don't know whether this is waste or well just sitting there. If you think 3,500 tons of indium in the tailings there, global indium production is 800 tons a year. We're talking several years of indium production sitting in the ground potentially. We don't know because we haven't quantified it. We are getting better at identifying and producing some of the critical metals. You can look at ratios of main to byproducts like rhenium to molybdenum, indium to zinc. Tellurium to copper has decreased, potentially because solvent extraction, electrowinning means you can't produce tellurium. Smelting, you can. So there's the way you actually process and refine and produce metal from concentrates is a real key factor in whether you get any critical metals or not. Economic decisions always certainly control what you do with your concentrates, where they go, but that doesn't relate to the critical metals. And this is something we need to think about somehow and change this sort of approach and thinking. Whether concentrates are sent to a zinc refinery that can produce indium depends on zinc economics, not on indium economics. And this kind of, we're not just talking about ramping up or doubling nickel production, annual nickel production. but we need to think about how we can make the most of the ore bodies we already have to ensure we can produce these critical metals, to have a chance of meeting carbon dioxide targets, and to also meet increasing demand that is, as I say, being driven by investors and consumers. It's not just all about climate change, it's about markets and seeing what people want and what they want to buy. And if we've seen at the moment with shortages and computer chips, that's affecting all sorts of things at the minute, that if you actually have significant decreases in supply of these commodities we take for granted, and that has real knock-on effects in what actually we can do with the manufacturing and the other end of the kind of the downstream part of the mining and manufacturing sector. Some people are probably saying, well, what about recycling? Recycling is a great idea. We recycle a lot. Some metals are eminently recyclable, steels, copper, and so on. But not all metals can be recycled. There's significant barriers to recycling of some metals. So if you think about your smartphone, the rare earth elements stuck in these things, the various other small amounts of metals or elements that we consider critical that are in these things. Now, how do we turn that and recycle these phones? There's billions of them out there, often just sitting in drawers because we don't know what to do with them, and they're ending up in landfill, and that's just a complete waste of the materials that are inside them. Product design means that a lot of the metals within waste materials are not designed for recycling. The European Union is legislating about this, but they're one of the few groups that are. Most waste electronic materials still end up in landfill. That means we're losing a lot of the metals we're considering critical. Equally, metals and minerals often can't be substituted for each other, which is another crucial point to mention. This is looking at end-of-life recycling rates. Some metals, these are the ferrous metals and the things like the base metals, nickel, copper, zinc, cobalt, iron, we recycle very well. We got the way they're used lends themselves into, they're very naturally recyclable the way we use these. Similarly, the platinum group elements, things like catalytic converters, are fairly easily recyclable these days. But then you look at these, look at all of the rare earths, look at things like gallium, germanium, indium, strontium, yttrium, scandium, lithium, especially with lithium batteries these days. We're still talking less than 1% recycling. That's improving somewhat, but it's still not improving at a rate that means recycling can contribute significantly to the rapid increases in demand we're going to see for these metals. There's potential. This is a paper in 2015 from Siachi et al. Looking at the potential recycling. So what we've got here is, if you look at neodymium, often used in magnets, we've got a little bit of in use and dissipated, which can't be recyclable. We've got a potentially recyclable sector, which is pretty large, and a currently unrecyclable sector here, which is basically areas for improvement. But the thing to note is that although we can potentially recycle a lot of this neodymium, we still recycle less than 1% of the neodymium we use. And that applies to a lot of these metals. Some of these metals we're approaching the amount that we can actually recycle. Some of these metals, there's a lot of potentially recyclable materials out there, but we're just not doing it for various reasons that I can go into. If people are interested, I can send them a paper or two after the talk. There's a few other challenges to think about as well. So, finding the mineral deposits we need is not always easy. Making the most of these deposits, understanding them, understanding the deportment of minerals and metals of interest, understanding how they behave during processing, geometallurgy, not easy again. Waste rock and tailings, if we mine more, we produce more of these. These need to be securely stored, and we need to make the most of them. Looking at, say, ultramafic tailings and waste rock for carbon dioxide sequestration. The minerals industry also faces a lot of environmental, social, and governmental challenges to mining, ensuring mining is as sustainable as possible. And this is, we need to mine more, but we need to mine it in a sustainable fashion. Otherwise, the minerals industry simply won't be allowed to mine in certain areas or exploit certain deposits. One of the key things, and this is kind of harks back to the IMARC protests in Melbourne a couple of years ago, NIMBYs and bananas. NIMBYs not in my backyard. I want the lithium for my battery, but I don't want you mining it anywhere near me. Go mine it somewhere else. Or bananas, which build absolutely nothing anywhere near anything. We don't need to build anymore. We don't need anything else. Stop mining. We don't actually need it. Both these viewpoints are fundamentally wrong. You can't have solar power, you can't have Tesla vehicles without the raw materials needed. So you need to accept that mining is required and that the metals need to be smelted and refined. And you can't just continue to ship it to other countries and give it, make it their problem. Because what happens is you get the manufactured products back for a huge number of, logistical, security of supply, cost, geological, and even things like social justice and exploitation reasons, as well as the value. Right? The value in mining is not necessarily in the raw materials coming out of the ground. It's in what you do with those raw materials. The value add comes down the mining chain. And if you ship the raw materials to somewhere else, they get the value. It's not just mining of metals, concrete and cement are real issues. Metallurgical coal, we're still going to need. There's some developments in this area, but these are all things to think about. These are all challenges and opportunities for the minerals industry going forward. Remember, the challenge is just an opportunity. That's something to remember with all of these things. And just starting to wrap up here, the bottom line is if you want to do anything meaningful about climate change, you need to mine more minerals and metals. It creates questions and problems and opportunities. Where we're going to find them from, we need to understand the geological processes that form the deposits. We need to increase our efficiency and efficacy of mining in terms of recovery and energy use. We need to mine other things. We need to mine landfills and mining waste. We need to be conscious of the impact that this metal extraction is going to have, the ESG challenges and benefits and risk that the minerals industry needs to consider going forward. How can we do this is the other question. We need to have open discussions with the rest of the public. They need to know how important the minerals industry is to their life. We need education, research, and discussion on all sides within and beyond the industry, with policymakers, stakeholders, anybody who's influenced by mining, and that, in other words, is everybody. And we're starting to think about this and do some of this at Geoscience here at UNLV, and that's one of the only plugs I'll have in this talk, but I need to have at least one. So if you've not already been convinced, every single person listening to this talk needs mining, and we're going to need more of it. The devices you're using right now are all, are all requiring minerals and metals to transmit the electricity, to transmit, me talking to you right now. And any sustainable future with reduced anthropogenic climate change, lower carbon dioxide emissions, is going to be built on the back of the minerals and mining industry. There's no point in having electric vehicles fueled by electricity generated by coal. That won't work. And if your immediate impact is, climate change doesn't exist and the world is moving this way anyway, and this is an opportunity for Australia to be a world leader. Demand for these metals is going to increase. Does Australia want to be the source of those metals? Or do you want to be a home of high-tech manufacturing? You want to keep the value add within Australia? The latter, there needs to be some rethinking of where these ores are processed and where the metals are actually produced from the concentrates and what that means for things like pollution, smelter development, and so on. Thinking about Australia, these are current major resources and energy commodity exports for 2019, 2020, and so on. Lots of iron ore, lots of LNG, lots of metallurgical coal, gold, copper, and so on. One of the things to think about looking at these statistics is, okay, well, what's going to happen with the change we're going to see? We might see decreased demand for LNG, in other words, natural gas, thermal coal, oil, and condensate. So you might see these export sectors decrease in value, but you'll see increases in value offsetting that by copper, nickel, lithium, aluminium, zinc, and so on. So one of the things to think about is that we're thinking about the future. So, it's not just the minerals industry, it's the kind of the economy of the entire country. And how are these changes going to affect that? One of the questions is, what's the future of gold? If people really get on a sustainability kick and actually think about, well, what is gold used for? It's used for investment, it's used for jewelry, maybe used a little bit in the chemicals industry, but it doesn't have the same sort of argument about it that maybe nickel and copper might in the future. You could probably argue that copper is more important as a mine than gold is, for example. So there's going to be some interesting arguments coming up into the future when we think about what's going to happen to the minerals industry globally. And this is just looking at thinking about value add from mining through to processing, manufacturing. This is diamonds as an example. This is essentially the material mined out of the ground. This is, if you think about this as copper, this would be the concentrate, this would be smelting and refining, and these would be the end products. And you can see the value add increases throughout the value chain through to this end. So that if you're just doing this, you're losing out on all this value add. It's not just diamonds. Like Mount Weld, the processing is actually taking place in Malaysia. Similarly, here in the US, the concentrates from Mountain Pass, just down the road, the rare earth element mine, they're being processed in China. So the question is, what implications does this have for the Australian economy? Should you be looking to think about value add, not just by mining more, but by adding some more of this downstream infrastructure and development actually in country rather than just exporting concentrates to China, Japan, and so on. We're seeing some changes. The Australian government has a roadmap for processing critical metals. Bingham Canyon shows the value of knowing the ore body and having an attached smelter because they're starting to produce tellurium. That tellurium production from Bingham Canyon, from the porphyry copper deposit, will pay for itself in more and more in 3 years' time. So in other words, they're making an investment, and that investment will start turning a profit for them in 3 years' time, and presumably will continue thereafter. But it's not easy being green. This is Jadar in Serbia. It's obviously going to be an incredible source of lithium if it gets developed, but they're feeling a lot of pushback on the social and environmental side of things. You can argue that, we need this for lithium batteries for our electric vehicles. But then again, local communities can say, we don't want it here. Go and get your lithium from somewhere else. So this is going to be an increasing conflict potentially going forward, and we're going to see more and more of it because we're going to see more and more demand for metals. They need to be mined somewhere. And one other thing in this mixture is policymakers. I mean, this is Joe Biden today talking about half of US cars manufacturing being electric vehicles by 2030. They say zero emission, but that depends on where you get the electricity from, of course. Global lithium shortages could put brakes on UK electric car sales, brownouts in New Mexico as a result of solar projects not being finished because they're essentially running out of materials like microchips and steel. So there's all sorts of complex interplays here. Policymakers can say what they want, but those targets may not be realistic, may not be met. And this is where we need to educate them and actually interact more with them and tell them about what they're thinking, explain to them what they're actually saying in terms of mining and materials usage tools. So this is my penultimate slide. What now? I'm going to say we need more conversations, discussions of this, and this is why I'm talking about this, not just so I can hear my own voice, but to try and get people thinking about this rather than just saying we need to reduce carbon dioxide emissions. We need more research, education, outreach, consideration of all of these things during policy development. We need more open conversations from all sides about this rather than ignoring it. The public needs to know the cost of being green, why mining is important in that being green. And you can talk all you want about how to combat climate change. You can talk all you want about policy to achieve it. If you don't understand and accept the mineral and metal costs of this, you're only halfway there. And that's my final 2 cents on this issue. What I will say is, just briefly, if anybody has any questions, they can ask now. They can email me afterwards. Happy to pass on papers, this PowerPoint. There's lots and lots of hidden slides in here as well, which is a bit of a jumble, but might be useful to some of you out there. But if anybody has any questions, I'm happy to answer them now. But if not, it's over to Nathan, I believe, right now.
Hi there. Thanks so much, Simon. It's a really interesting overview of certainly the work that you've been doing and certainly sort of the forward projection, I suppose, of this sector. Certainly, we've had quite a few questions already come in online, and I'm sort of happy to pose those to you now. But certainly, for those of you online, please follow up directly with Simon if we don't get around to some of your questions straight away. So thanks again, Simon. I've got a question. I'm going to start with a question from Nita Babaka-Fox here at the SMI. You mentioned that critical metals end up in many cases in the waste. What mapping activities are being undertaken in the US to identify this potential value? An example from some of Anita's projects here in Australia, there are significant efforts being undertaken to understand secondary prospectivity, particularly in relation to new economy, metal kind of prospectivity in mine waste, particularly in partnership with METS companies. So looking at those valorization pathways, do you have any initiatives in America that you can draw on that are being carried out at the moment?
There are things going on here for sure. Let me think. The Bingham Canyon being one, certainly the tellurium extraction there, which is going to come on stream over the next couple of years or even this year. I know Nevada Gold Mines and Barrick thinking about specific projects both here in the US and globally in terms of just assessing what they have in terms of known mineralization and byproduct and co-product potential. The USGS is doing some work, but compared to, say, funding like the Western Australian Geological Survey and so on, the funding the US has is pretty small, and it's mainly focused on new deposit potential and so on. Department of Energy, Department of Defense are funding some small individual projects through national labs and with individual producers, but there's no kind of whole-scale effort. It's dribs and drabs, and people are slowly becoming aware of the problems and issues and the value that could potentially be produced from this byproduct and co-product extraction. But there's a long way to go. I mean, I've got a postdoc working on tellurium at the minute, and he's encountering a lot of surprise in industry here in the US and elsewhere when we start talking about, well, we think you've got this amount of tellurium in your deposit. And I said, oh, okay, tell us more. And when you start talking about numbers, then they start getting interested, especially if those numbers compared to their kind of all-in sustaining cost of the like. So there's a lot of potential out there, and there's much more to do. It's piecemeal in essence.
Okay, thanks, Simon. That's good. We also have another question here from the SMI from Deanna Kemp, just talking about the kind of major market changes you may envisage in the commodity, in these commodities in particular. So given the critical metals and mere byproducts, can you comment on the role of states or shareholders or investors, and will they require producers, and probably similar to what you're talking about there with the tellurium example, will they require producers to define reserves and resources of these elements? Can you talk us through some of the unusual market trends that you may see on the horizon as well?
So the one potential thing that could happen, and this very much depends on how things pan out, is that some of these metals may well go from kind of minor parts of the minerals industry to more major parts. There's a good paper by John Sykes and others a few years ago assessing the potential for I can't remember how he termed it, but basically the potential for these things to not to get to the level of copper, but certainly to become a more major player in the minerals industry, just in terms of the value of that sector. I think reassessing and thinking about that with the changes and expected changes we're going to see could be quite a nice little study just to work out, well, you know, which of these sectors are likely to be able to stand alone and be of interest to major mining companies. The byproduct thing is an issue. If you want companies to report this, if you want companies to report reserves and resources, you need to change the way, you need to change things like JORC essentially. Because at the moment, you know, the JORC has value limits to what you can include in resource and reserve reporting. Those value limits are probably higher than the value of a given byproduct. If you clustered all the byproducts together and said, well, this is the byproduct value of this in this reserve and resource, that might be a little different. But I think there needs to be some thinking about, if we want to get serious about understanding where things are on a global scale, not just on a single deposit scale, then I think we need to think about changing the way we report things. In terms of unusual market trends we see on the horizon, that's a difficult one. I think what we know is, or what we think is going to happen is, you know, we're going to see significant demand in lithium, graphite, and nickel, and so on. Right? We know if things continue on as they are, that's going to happen. There's no reason to say that that won't continue in the same way. So what we're going to see is potentially, eventually we might see prices increase in those metals as supply, is outstripped by demand. There's some interesting things going on in lithium at the minute. Jadar is going to be a big player. It's going to bring 40,000 tons of lithium a year onto the market if it gets up. But Rio Tinto is slowed down the development of that project because they looked at the lithium market and they said, well, if we developed this a couple of years ago, we're going to saturate. So we're going to slow things down and wait for lithium demand to pick up. And I think there's this interesting interplay between predicted demand and actual demand, and predicted supply and actually bringing things online. But the trouble here is that there's so much time lag between finding something in the ground and actually turning it into a mine that we could end up in situations where demand is far outstripping supply, and we can't do anything about it unless we really change even the way we enable mines to be brought on stream. So I think I'm not sure I've entirely answered your question, but I think there's just this really fine balance at the minute. I think everybody's waiting to see what happens. But the thing is, if we wait too late before really looking at these problems and looking at this potential demand, then we're going to end up with a demand really outstripping supply, and that could be a mess for all concerned. So I think we need to think about forward planning a lot more. We probably need to think about the way we actually enable mines to come on stream and become developed. So things like that.
Thanks, Simon. I guess one of the things here is that it wasn't that long ago that critical metals also used to be referred to as strategic metals, and I guess there's a lot of strategy involved in relations around markets and global, I guess, relationships with China, for example, and controlling supply as well. So I suppose we need to be more strategic as countries that want to perhaps replace import with own production in some respects.
And I just also saw Anita's comment on Richard Harrington's recent article. It's a good article and a good letter or so he had as well, but it's not exactly news because we've known about this for 4 or 5 years now. And I think it's good to get words out there, but I think there's been a lot of people talking about this for a while now, but I don't think we're doing a very effective job about getting into the minds of the general public what climate change mitigation means. But anyway, that's me just jumping into the questions.
No, that's good. There's quite a few coming in, so I'm not sure how many more we're going to get through. Certainly, there was a follow-up question from Deanna as well, which we might pose to you separately. I guess that we had another one here from also from the SMI, just in relation to the circular economy modelling. I just wondered if you could touch on that quickly. From Marcin Zemski, are you aware of any circular economy modelling to assess how much extra carbon needs to be emitted to generate the specialty metals in order to drive the new energy economy? So
the two World Bank reports that I've mentioned here, there's one in 2017 by Drexage and another one in 2020, and I can't remember the lead author. Their calculations on the carbon dioxide emissions include costs for the extraction of the metals required. So it's not just saying, well, this is what, this is the energy mix we need. They actually, I believe, in their modelling incorporated the carbon costs for the extraction of mining given current mining assumptions. So there's been a little bit of that, but I think there's much more to do in that area, especially if we, there's a lot of assumptions in that modelling that the World Bank has done, including that, the fact that I'm pretty sure they haven't incorporated the fact that carbon dioxide emissions increase as grades decrease. And if we're going to do more mining at potentially lower grades, there's going to be an awful lot more carbon dioxide emitted and the like. So I think there's much more to do in that area to think about, well, how much is all of this going to cost in terms of carbon dioxide emissions and so on. And then equally, things like mining ultramafic rocks, how much carbon dioxide is going to be sequestered just by naturally leaving it out as tailings, and how can we enhance that? So there's good work by Sasha Wilson and others in that area.
So on a related note, Consuelo Garcia is just asking if you can comment on the main environmental challenges in the future, increased production of energy, transition metals, or I guess beyond CO2, what other factors are we facing here?
The traditional environmental challenges of mining, so acid mine drainage, issues of ground and surface water, issues with tailing storage, secure tailing storage, issues with land use, issues with the pollution from smelters and refiners and so on. So if you imagine all the traditional environmental challenges we have in mine sites now, then double that because we're going to be mining much more. So there's also, I don't see there's any differences in extraction of certain metals and minerals. Lithium brines might be one example where you might need to think about things slightly differently. But I think basically what we're going to see is you're going to see much more of the environmental challenges we see now, only much more because you're trying to mine more, you're trying to bring more mines on stream. There's going to be all sorts of things like land use conflicts and so on. So I don't think there's going to be any major change in environmental challenges, but it's going to be much more of what we're encountering now and what we're not effectively dealing with in a number of cases.
Okay, that's good. Thank you. In terms of time, we are running down. There are a few more comments. I might just touch on this one because it's probably going to be a growing area of I guess growth in critical minerals. so I can't see the full name, but Fitzum asked a question here, just in terms of the increase in demand, and potentially a significant amount of these minerals could be found in Africa. How do you think policy changing in countries like the DRC might affect supply going into the future?
I suspect it's difficult to say, but you might see more resource nationalism. I mean, we might be seeing that with the change of government in Peru at the minute. It may be that a certain number of countries see, increased interest and demand for their metals, and as a result, they may start to actually try and make more of those, the metal extraction in that country for their own benefit, which is a natural and a good thing to do. I mean, if all you're doing is you're shipping off value elsewhere to a multinational country or to some other country where the metals are produced, then I think resource nationalism and dealing with inequalities in a better way is certainly going to be an important thing going forward. There are other influences like the Belt and Road initiatives from China, meaning that China's going to be very influential in a lot of these areas because they've put money in already, and that money buys influence, sadly. But it's going to be interesting times in terms of what we see on the kind of political side of things. But I think we will see a lot more. If there's a lot increased demand for metals, increased prices for metals, we will see a lot more resource nationalism. And that's just a natural occurrence of a country like the DRC being pretty well endowed in certain minerals that the rest of the world thinks are critical and important.
Okay, I'm going to close off on one last thing, which is kind of important. I guess there's an underlying theme in your presentation, but it's kind of a few people, Pat, Heyman, Anita, and Deanna have also touched on this in terms of communication and communicating, particularly to and beyond just the people that are kind of the not in my backyard type people. How do you go beyond that? How do we actually communicate this to the public and educate the public about the necessity? I guess it's a cyclical question going back to the necessity for mining, but I guess a specific relationship here to critical metals, given that our kind of daily life is underpinned by these elements.
I think we need to maybe take a leaf out of farming's book, because everybody thinks that farming is crucial, which it is. Everybody thinks that farming is beneficial, but everybody has this view of a farmer as being somebody who doesn't destroy land, who doesn't have any really negative environmental or other benefit or other impact, and produces the things we need. I'm not saying we should greenwash mining, but I'm saying that if we can start to educate people at all levels, from high school and earlier through to university, and increasingly, policymakers and the like, just try and tell everybody the importance of mining. I'm not saying, as I say, we greenwash mining, but I'm saying that we just have an open conversation about, well, farming is really important, but it's also problematic environmentally. Why can't we say the same for mining? Mining is really important. It's environmentally problematic in some ways, but this is how we're improving and what we're thinking about into the future. You need mining as much as you need farming. So why can't we think about these things in the same way?
I think we need more case studies of successful remediation. I think certainly the work that's done at the SMI highlights that very few mines have actually been remediated. And I guess we don't set a very good legacy example of how we can actually close mines effectively, let alone open new ones and mine them.
What the minerals industry needs to realise is that if you mess up, then that messing up creates huge negative headlines for everybody. You just look at Juukan Gorge as one example of that, and that's that was the tailings dam failures in Brazil. These are single events, but they have global consequences. So, and the minerals industry already has a bad reputation in quite a lot of places. So we just need to recognise as a community we need to do better.
Absolutely. Well, there's some good discussions to keep going, I suppose. Thank you everyone online for joining. Thank you for the questions, Simon. You can see that there's a few questions there that are unanswered. We might get a transcript of those and maybe we can ask you to address some of those if you've got a bit of time, but that'd be great. I don't know if you wouldn't mind just progressing the next slide just so I can show you next week's seminar. That'd be great. Because it's a related theme. So hopefully you can join us next week for the JKMRC Friday Seminar, Friday the 13th of August. We're really pleased to have Alice Strasser-Bosco from QUT, and she's going to be talking about renewable energy technology and more specifically the adoption of that in the Australian mining industry, which I think is really an important and related theme here. So hopefully you can join us then. because of the lockdown here in Brisbane, it's very likely to be online, but otherwise we'll announce that close to the date. So, Simon, thanks again for your talk today. It's been really really good having you involved, and thanks everyone online. So we'll close off now. Thank you. Thanks, Rick, for joining us as well.